So we showed in the last lecture that any transfer function can be written as a ratio of polynomials, and it's also true that any polynomial can be factored as long as you know its roots, where it is equal to 0. And we can expand about each of those, and we can write it as a product of s minus that root value. And if we have roots in the denominator polynomial, those are actually poles of the function. The function will blow up there if s equals exactly that value. So the key to understanding the behavior of f of s is to know what all these values of the roots are and the poles. And so let's consider the example we had in the previous PowerPoint, in the previous lecture, where we had the gain, the voltage gain equal to, where this was a capacitor and a resistor in series leading into an inverting op-amp, and then the feedback op-amp was just R2. And we found this function of s in the frequency domain when we plugged in a particular s. And notice that we have two first-order polynomials. The first, the numerator has a pole at 0. So s minus 0 is s. The second has a pole at s equals minus 1 over r1c. So if we plug in minus sign there, pull the minus sign out over here, we get that function. And so we can then consider what happens when omega goes to 0. So when omega is very small, in that case s is small and the 1 over r1c dominates. And so if we pull that out, the r1s go away, c comes up in the denominator, and we're still left with the omega here. So if we take the magnitude of this, the j doesn't matter, and we get something that goes to 0 as omega itself goes to 0. And then when we look at the phase, we see there's a minus sign and a j, which is minus 90 degrees, or minus pi over 2 is the phase. Now when omega goes to infinity, we can again we can now neglect the 1 over rc factor, because s is going to be much bigger in magnitude than it. And then we have s over s, as here that becomes 1. And when we do that, we're going to just get something going to minus r2c. You see here I've factored out the r1c out of this. And so we get something that goes to a constant. And its phase is going to be just the minus sign, the j's cancel, and I get minus pi. Finally, if I'm right in the middle, where s is the same, where omega is the same magnitude, but opposite sign of the pole, now the two terms are of the same size, and I can just plug them in. Again, I get minus r2c, but I have j over 1 plus j, and this has a magnitude of square root of 2 of the top. So I'm down from that peak by 1 over the square root of 2, and my phase is in between these two. It's minus 3 pi over 4. So we can break down each of those factors in my transfer function and find a characteristic response of it. So imagine that I have this particular factor, s minus some root or s minus some pole, and I can write that then as an imaginary part. I just plug in j omega minus r. Here I'm imagining a purely frequency-dependent value for s. And I can write, this is now a complex number as an imaginary part and a real part. And I can write that in the normal way where I have a magnitude and a phase. And I've actually drawn that here. Here's some pole p sub I. It has an imaginary part, which is the j omega, and a real part, which is negative in this case. So if I put all my phases in terms of this way, then I'm going to have a bunch of magnitudes all multiplying and a bunch of phases which I'm going to add, right? So I multiply all the m's of the numerator magnitudes. The denominator polynomial has its own magnitudes, which are all n. So I have some number here that's a real number. But then the phases all add up, and I add up the ones in the numerator and subtract off all the ones in the denominator. So I can then think, okay, let me take the log of this thing, and so that's going to be the log of k, that's just some number, and then I'm going to add up the numerator magnitudes, subtract off the denominator magnitudes, again, log of each, right? If I take the logarithm of this, I break the product up into a sum, and then the exponential goes away and I just have the phases adding or subtracting as like. So the reason we do this is we can plot the frequency on a log plot, and as a function of the log of s, though that doesn't show up here yet, and that means we're going to add components. We're just going to add up a bunch of things, either in the phases or in the magnitudes, to see what's going on, right? We plot it on a log plot, and we're adding in logarithmic parts, and that's going to make our function fairly easy to understand. So just to illustrate this again with our example, again we have this gain, right? I go through the calculation again here. It's R2 over Z1 minus that, and then I make a polynomial in the denominator by multiplying through by CS, and then I factor out. Here I have a constant in front, and I have polynomials with s in them here. And again, there's a root on the top of 0, a pole on the bottom of minus 1 over RC. So the magnitude of the top is just going to be omega when I plug in j omega. And the magnitude on the bottom is the pole squared minus omega squared. That just tells me what the magnitude of n is here. And so I can imagine now what's my psi angle as I go from this root up to some value of omega. My psi is always going to be pi over 2 no matter what, and my magnitude is just going to be omega. Whereas from the poles are often illustrated with crosses. I'm moving from 0 as omega goes up here, so the magnitude is going to grow. It's always going to have a p1 squared in it, but then it's also going to have an omega squared. I take the square root. That's how I get this magnitude. And the phase goes from 0 to pi over 2 in this particular fashion. So combining all these adding of things, I can use all this to motivate how I can quickly add together all these components to draw and sketch the response. And these things are called Bode plots, and they're always drawn with the logarithm of the frequency on the x-axis. We'll use base 10 always, and the logarithm, but in a decibel scale on the y-axis for the magnitude of the function. The phase will actually draw on a linear y-axis because we'll want to go from minus pi to pi for the phase. Now, decibels are usually described in terms of the power put through, rather than the amplitude put through. Now, the power is proportional to IV, or V squared over R, or V squared over Z, or I squared R. So there's a square in it, and therefore if I'm taking the log of something squared, I get double the change in the log. So therefore we're going to say that a decibel change of 20 in the power corresponds to a factor of 10 change in the amplitude. And so we're going to see 20s a lot in the decibels. So here's just a definition of that. If I have a gain in decibels, I'm saying the ratio of power, take the log 10 of that and multiply by 10, but that's the ratio of the voltages squared, and I pull out the square out of the logarithm to get 20. Okay, so let's just go through the steps. We've showed much of this already. So I express my transfer function in this form. This is slightly different than I had before. Here, A1, A2 are 1 over the poles. They used to be over here. And to do that, I had to factor out a lot of things into K. And notice I've also arranged them in order, A1 from A1 being the biggest, in other words, the smallest pole, to AN being the smallest. At the end, AN, being the smallest, being the biggest value of the pole. Likewise in the bottom, I've arranged them in order, and I'm going to want to go through them in order. And so if f of 0 is defined, in other words, if A1 is not equal to 0, it could be, then I can find the value of the frequency at 0. That's just going to be the absolute value of K. And I can find the phase there as well. This is just plugging in those. If A1 equals 0, which I actually mean that 1 over A1 is 0, then we're going to need to evaluate this at some very small value of omega, because it's not going to have a value at omega equals 0. So now I just go through in order of the poles and go through and add a thing for each. So every time I come to a root, I make the decibel, the slope of my response function in this log plot go upward 20 decibels per decade more, with a kink in this value at the root. And then I also add a change of pi over 2 in the phase. And I divide that. I start at 1/10 of the root value, and I continue, and the change is complete at 10 times the root value. For the pole, things are different. I add a kink downward of 20 decibels per decade, and then I make a negative change of pi over 2, again going from 1/10 of the value of the root to 10 times. And remember, the frequency is on a log plot, so these are symmetric about the kink point. So if I just have one root or one pole, I can easily say what this does. So if I have one root, not at 1 over A equals 0, then I have a gain of 1 previous to that, if that was so. And then once I get to the pole value, I start going up at 20 decibels. There's my 20 decibels per decade. Here's 1 decade. So I add a kink going up. And my phase started at 0, by definition, in this case. And then because I have a root at 1 over A, then I make my change in pi over 2 from 1/10 to 10. And I go up. So whatever I started with, I had a kink going up like this, and a phase change going up like that at 1 over A. The poles just do the exact opposite. I start at a pole, I started along, I hit my pole, and I start going down at minus 20 decibels per decade, and I make a phase change of minus pi over 2. So let's work out the example. Same example we had before, but now I'm going to plug in values, and I can only make 2 choices. I can only choose 2 of the 3 components. The third one won't matter. And so in this case, I'm going to give R2 being 10 times R1. In other words, I sort of expect a gain of 10. And I'm also going to make R1C equal to 1. That defines some frequency scale. So I plug that in. Here's the equation I had before. Notice that rather than having 1 over something here and s there, I have R1C s here, and these factors are all adjusted likewise. And so I know R2C is going to be 10 from this. The minus sign comes around. And because R1C is 1, I just have 1 plus s in the bottom. So A1 equals infinity, meaning there's a pole at 0. And B1 equals 1 because of the factor there. It's actually minus 1. And so now I do have a pole at 0, so I have to pick some value. I'm going to pick omega equals 1/1000th, much smaller than the 1 here. And when I do that, I plug in, and I get my minus 10, j over 100, j over 100. I can ignore this one. And so basically I get minus 10 j divided by 100 divided by 1. So 10 over 100 is 1/10. The minus sign comes and I'm left with the j. So I expect that my magnitude at 1/100th of is going to be minus 10. So that gives me this point. Minus 10, 1 over 10 there, is minus 20 decibels. Right, so that gives me this 1 point. Now I know that because of this s, I know that I'm already past it, any positive value for s, so I'm going up at plus 20 decibels per decade. That gives me this slope. Here I'm minus 20, so at 1/10 I'm going to be at 0, and at 1 I'm going to be at plus 20. Then I hit but that's 1 at the B, so now I add in a kink downward of 20 decibels per decade, but I was going up, so I was going up, I add in a minus 20, that flattens me out. So I've added in from the pole here this kink. Also, I started at minus pi over 2 from the pole, and then from 1/10 to 10 I add in this minus pi over 2 change, added on top of the minus pi over 2 I started, so I go to a phase of minus pi. Okay, so I can now compare this to what happens if I plot everything exactly and take the magnitudes. And so here I've just copied down everything I had before, and so the red line is what I drew before. What actually happens is that I get the blue line coming out. And we can actually adjust our Bode plot with straight edges by putting in a point at the pole value here that's down by 6 decibels. 6 decibels is 1 over the square root of 2. So the fact that I'm lower by 1 over the square root of 2 of the maximum means I come down there. And now I can just round this out a little bit if I know that 1 point being down. And here's the phase as well, so you can just sort of imagine that the phase works in there.